The Europa Rocket is Project Jupiter entry in Spaceport America 2021 and represents the biggest technological leap the project has ever taken since its inception in 2015. Europa's design has been in development since 2019, and it was originally intended for SA Cup 2020. In the aftermath of the event's cancellation, it was later improved for Latin America Space Challenge 2020, allowing the team to score 3 different awards including Overall Winner and Technical Excellency. For SA Cup 2021, a lot of changes and upgrades were made, including better electronics, a larger payload, improved aerodynamics, among other things. Europa is a 3.5 meters long rocket with a diameter of 5 inches. Its fuselage can be separated into 7 different parts, a carbon fiber nose cone, followed by 4 different modules, a hybrid motor, and fins. In the rear section, the motor external structure is visible, being part of the fuselage. The nose cone was optimized to minimize drag in subsonic and transonic regimes, using a von Karman shape. Each of the tubes is hand-built, using a lamination process with epoxy resin and carbon fiber. The fins were also enhanced to minimize drag. They have a NACA 0012 airfoil section applied to a trapezoidal shape, giving the rocket a stability margin of 2 calibers. Finally, there's a circular arc-shaped tail to minimize drag. Unlike previous rockets, which counted with 2 parachutes, a main and a drogue, Europa will have a single-rift quarter-spherical main parachute and a pilot chute. The pilot is attached to the main's deployment bag, aiming its ejection. At apogee, the main will be riffed, with a diameter limited by the riffing line. Its total drag is reduced, and the rocket speed decreases with more stability at high altitudes. As the altitude decreases, and the rocket reaches a predetermined level of 1400 feet, our riffing cutter is activated, cutting the riffing line and allowing the main chute to achieve its total drag, greatly reducing the vertical speed until ground level. The parachute's ejection system is composed by a pair of 25-gram CO2 cartridges fitted to aluminum cylinders. Inside each of the cylinders, there's a puncture and a small charge of black powder. At apogee, the black powder is ignited, and the punctures break each of the cartridge seals, freeing the compressed gas, pressurizing the module, and separating the rocket nose cone from the rest of the fuselage, ejecting both the main and the pilot chutes at once. The ejection system was already tested many times before, including in-flight tests. The riffing system was also tested in-flight in our rocket Themisto, although some improvements still need to be tested. The electronic subsystems are responsible for detecting the correct moment to activate the ejection system and to trigger the disriffing of the parachute. Its structure is divided accordingly into those 2 individual parts. The first part is located below the parachute ejection system and takes care of the initial parachute opening. It contains 2 redundant altimeters to detect apogee with high reliability. The primary system is a commercial off-the-shelf RRC3 altimeter, and the secondary system was developed by the team and counts with a BMP 280 barometer and an STM32 that runs a normalized least mean square adaptive filter to calculate the apogee. Both systems have already been tested in previous flights and have succeeded. The second job of the electronic subsystems is to start the main parachute disriffing. The riffing cutter is divided into 2 parts, the activation system and the cutter itself. On the one hand, the activation system, which is placed inside the nose cone, contains the detection's electronics, an RRC3 and a SRAD detector that operates redundantly. On the other hand, the cutter itself counts with a combustion chamber, through which the riffing line passes and is attached to the main riser. The student researched and developed detector contains a BMP 280 sensor and an Arduino Nano to perform the calculations needed. Below the electronics, there's the payload module, whose structure is easily removable from the rocket. It weighs 4.3 kilograms and carries 3 major parts. First, there's the telemetry system that captures and transmits data on acceleration, angular speed, air pressure, GPS location, among other parameters. The second system is a camera, which records the flight. Finally, there's the main experiment, which is a controlled inverted pendulum. This experiment was chosen for the notable importance of control in space systems. For this reason, it was envisioned with the aim to promote and provide aid for future control projects that the team wants to develop. For example, it should provide a clear vision of the disturbances any control system on board the rocket would have to withstand. Its main goal is to keep the pendulum in a position perpendicular to the module's structure, and therefore align it with the radial symmetry axis of the rocket. For it to work, the team not only modeled the dynamics, but also projected a continuous time controller, which was later converted to discrete time. The control algorithms are implemented in a microcontroller, which controls the pendulum through the use of a DC motor. Finally, it's worth to mention that, although the experiment involves movement during the flight, it's not expected to affect the rocket's flight dynamics in any way. Europa's hybrid motor, named Marimbondo, is an M-class motor of paraffin and nitrous oxide, and represents the final result of over 3 years of development. Essentially, the engine can be divided into two segments, the oxidizer tank and the combustion chamber. On top of the oxidizer tank is connected the bulkhead with the venting system. On the bottom goes the injector, with a direct connection to the combustion chamber. As the oxidizer goes through the injector and enters in contact with the paraffin, the burn will be maintained. The expanded gases on the combustion chamber will then be expelled through the graphite nozzle. During the fueling process, as the oxidizer is being fed, the feeding tank and the injector are connected by a feeding line, ending in a polymeter hose wrapped by a solid propellant grain. After the ending of the feeding procedure, the grain is ignited, allowing the oxidizer to flow towards the combustion chamber and initiating the burn. The motor has been thoroughly tested and analyzed. The overall thermodynamic process of fueling, the cold flow, and the flight regime were simulated using in-house software. The structural and flow simulations were done using finite element software. The hydrostatic pressurization, hose burn, and communication tests were completed. For the static tests, new installations were built on USP campus of Pirassununga, but as the quarantine started just a couple of weeks before the test, it has been postponed indefinitely. The trajectory of the rocket was simulated using RocketPy, a in-house software. Europa has a predicted apogee of 10,421 feet, achieving it at T plus 27.3 seconds. Its maximum velocity is of 773 feet per second at approximately 0.7 Mach with a maximum acceleration of 5.5 Gs. So that was the poster session and a quick overview of Europa, Project Jupiter next rocket. Thank you for watching.